Now we've looked at the server side. What about the client side? Well, on the client side, it's just as much of a mess as on the server side. So we have all kinds of scripting solutions running inside of the browser or outside the browser. And in the past, we've seen that some solutions have grown to be popular, just like on the server side. We had CGI bin, which was CGI binaries that were very popular, but then the popularity declined. We have the same developments on the client side, where some solutions emerged, became super dominant, and now have disappeared completely. And we're going to see a couple of them just to cycle through them. And one example is the Java applet, which was basically a compiled Java program that was downloaded in your browser. And all of the resources that it accessed were regulated by some Java security manager. Anyway, this is now dead. And it's dead, and so is the Microsoft counterpart, which was ActiveX, which didn't run JavaScript, which was nicely supported by some security manager. It just ran native code without any security manager. So ActiveX was running native code, so it's very efficient inside your client, and it had in principle full access to anything it wanted to have, the entire environment. In that sense, it was not a very secure solution, and you could only allow this to happen if you trusted the source of the code and you trusted it to be secure. Anyway, this is also dead. What is very much alive is the plethora of scripting languages that we have today, of which one is clearly the most dominant one, and that is JavaScript, or Microsoft's version, JScript, or ECMAScript, which is the standardized version. But it's not the only one. There are others also. So there's Visual Basic Script also. Okay. Now, the JavaScript was something that was initially introduced by Netscape, which also built one of the prototype, the important browsers that nobody ever talks about anymore. Okay, and but it's definitely survived that browser. Another thing that is, and we'll talk about JavaScript later in more detail, and the security policies. Another thing that's dead is known as Google Native Client, which is unfortunate because it was a very nice way for me to introduce software fault isolation, which is still very much alive. So even though Google Native Client is dead, software fault isolation is being used certainly in lots of research projects. And software fault isolation makes sure that even if you run native code, so Google Native Client, or NACL, allowed you also to run native code inside your browser, but securely. So unlike ActiveX, it made sure that this code could not access resources that it shouldn't access. That includes data, but it also includes, for instance, other code in say, your browser or so. Okay, it was a really cool solution, and it's now dead. And the reason for that is that there are other solutions that are more portable and also offer similar performance. Because nowadays what we have is for instance WebAssembly. So this starts with ASM.js, which was a subset of JavaScript that allows for very fast code, right? So if you use that subset of JavaScript, you can compile this into very efficient code, near native performance. And moreover, what you can do is compile code in languages such as C into ASM.js, and you would get then this fast, efficient code execution inside the browser of the client. Very attractive, allows you to do all sorts of cool things that that would be difficult with the performance of interpreted scripts or so. And WebAssembly is a low-level bytecode format that allows you to do this efficient in-browser code execution. Okay? And its initial implementation was based on the feature set of ASM.js, and it has, similarly this attractive property that you can support compilation from C and C++. That was the original aim there. Okay. Now, I don't want to say too much about WebAssembly. Maybe we'll talk about that in other lectures. But I just want to emphasize this. So suppose it's completely secure, right? And you're not allowed to access any resources that you shouldn't be able to access, code or data. Does that mean it's safe? And it's problematic. This is not entirely clear, right? So because there are other threats that we never really took into consideration. We talked about confidentiality, integrity, and availability, and it all makes sense, right? That's all. Those are all important properties for security. But there are other things also, and in this particular case, the performance of WebAssembly was actually making it attractive for attackers. Because what attackers could do is run code efficiently in clients' browsers, um, and exploit that to make money. For instance, by doing cryptocurrency mining inside a client's browser. So you would have a website where the user would stay, maybe something that showed sports events or so. And while you're on this website, there's actually JavaScript running in your browser, mining cryptocurrencies and generating money for the attacker. So even though it doesn't steal anything, so there's no confidentiality breach, it doesn't change anything, so there's no integrity breach. It doesn't make your browser or website unavailable, so there's no availability breach. It still partakes in some malicious activities, right? So it generates money for a criminal, and what it's stealing essentially is your computing resources and essentially your electricity, the payments, the money that you pay for your electricity bills. It actually it means that you're paying partially for computation for cryptocurrency mining for an attacker. Okay, we wrote a paper on this called Minesweeper, and the idea is really simple, right? So we looked at how often this happens and what the profits are. You go to a website, and the website gets in the background stealthily. It loads some mining payload that starts doing cryptocurrency mining that actually leads to the pockets of the criminals being filled with money, even though you may not even be aware of this. So, and this is actually crucial because it's an attractive proposition for the attacker. Unlike in the past, where we had malware that transferred money directly from your bank account to a criminal's bank account using your internet banking capabilities, or ransom, which is actually visible, right? So you're actually starting to lose money, and the bank may see that there's a strange transfer, but you certainly at some point are going to realize, look, there's a transfer of 1,000 euros from my account that I have no recollection of. Something is out of the ordinary. It makes the attack visible. Okay? The same is true, for instance, although slightly lesser extent, for ransomware, where ransomware encrypts the data on your disk and says you can have it back if you pay me, right? In that case, you certainly notice it, so it's visible in that sense, and you pay willingly to get your data back. But at least it's not visible to the banks, right? So the back end of the financial system is not going to notice any transfers that are really out of the ordinary. It's not going to receive any complaints from users about this either. So it's a little bit less visible. But now this cryptocurrency mining is even less visible because there is no connection. There is no money from your bank account stolen, or a payment that you willingly make and transfer money from your account to a criminal. There is no transfer of money. There is generation of money, and that means that the criminal is flying under the radar even more than before, right? You're paying indirectly with your electricity bill and with less resources available perhaps on your machine. In that case, it would be slight reduction of the availability. Anyway, that's cool stuff, and it's profitable, at least for some popular websites. You can see that they make some tens of thousands. This was a couple of years ago already, some tens of thousands of dollars per month. Okay, great. Now we've talked about client-side scripting, and we've seen that JavaScript is super popular. How does that work? Well, you can embed your JavaScript in your web page by a script tag. So you simply say, well, what is coming next is JavaScript, and the JavaScript in comments tags will basically have some assignment to variables from something that that interacts with the user. So you can ask for I don't know, input from the user, and then have control flow that decides to do this if the name is filled in, do something else if it's empty, and all sorts of other things. Okay, so that's what scripting is all about, and what the script can do is interact with the browser and the document. Okay, so the document object model allows your script. Here's your script to interact with the document, the content of the document, and the browser object model allows your script to interact with the frames or the location, and we'll talk about Ajax later. Anyway, with elements of your browser. Okay, let's zoom in on this. So we have a document object model and a browser object model, and the document object model is essentially a programmatic interface to the content on the page, right? So you can, for instance, have something like a new horizontal rule which you append at a particular place in your document. So you're looking for an element in your current document which has been given the name insert horizontal rule here, and there you append your new horizontal rule. Likewise, you can manipulate the browser object model, for instance, to modify the location that you're currently at. Okay, so what about security? You're allowed to access browser content and the document content, but surely there must be limits to that, because otherwise your JavaScript would be able to access many things on your computer, and certainly also many things from other web pages. Well, so you're downloading this JavaScript, but there the things that the JavaScript can do in your browser is limited by means of sandboxing. So, for instance, your JavaScript doesn't have access to files. It doesn't have access normally to network resources. I'll talk about Ajax in a bit. And it doesn't have access to a number of other things. And the precise details of the sandboxing may vary from browser to browser. But there's one other really important thing, and that is a security policy. And there are different types of security policies, but I want to discuss mainly the one that is here at the top, the same origin policy. It's I think a really crucial part of the security of JavaScript execution. And the same origin policy mandates that the JavaScript can only access the resources that are associated with the domain of that JavaScript. So if you're going to a website of, say, I don't know, bankofamerica.com or barclays.com or what have you, the JavaScript of that website can only access the resources, such as the cookies of bankofamerica.com. And the bankofamerica.com script will not be able to access the cookies of barclays.com. In other words, they have to have the same origin. There are other policies. For instance, you could also have signed script, where you have different allowances for scripts that have been signed by the right principal. Or you could have a configurable policy where you manually modify a policy file, and all of that works, right? But the main thing that is universally applied across the browsers nowadays is the same origin policy. So what does that mean exactly? Same origin policy? Well, it basically means that every frame in a browser's window has an origin, a domain that it's associated with. And like I said, the web browser permits the scripts in a page to access only the resources of other pages or this page if they are from the same origin. Okay? And the same origin, strictly speaking, means that they have to have the same scheme, for instance, HTTP or HTTPS, the same host name, the same server if you want, and the same port number. Okay, and that means that you cannot easily access, in the absence of vulnerabilities, the resources of another web page. Okay, so that's what the same origin policy tries to enforce. And what does that mean in concretely? Well, let's look at an example. We have something that that is associated with HTTP www.example.com and then some other stuff. What is the same origin? Well, if it's exactly this one, which is, let's see, the same exact same page, that's of course the same origin. If it's slightly different, but you have a different directory only, it has the same protocol, the same server, and the same port number, and the port number implicitly is port 80 at this in this particular case. That's successful. However, if you change the port explicitly, it's not allowed. You cannot have access to the resources corresponding to this page. Okay, you cannot, or depending where the JavaScript corresponds. So if this is where the JavaScript corresponds to, it cannot have access to the resources of this page, right? Nor to the resources of this page, because here the protocol is different. So it's gone from HTTP to HTTPS. Okay, nor from this one where the host name, the server name, is different. Okay, so it's no longer www.example.com, but even example.com, where the www is left off, is taken as a different domain. So this is not allowed. Nor is a different prefix to that domain considered to be the same host. So it's a different host, and it has to be an exact match. So the same origin policy, if this worked perfectly, would already, and it does already, prevent many of the attacks. Just to provide a little bit more detail, if you include on your website an iframe, then the iframe can only access the resources associated with that domain. However, if there is external code that is referenced in that iframe, so you're executing a script here, okay, within that iframe, that script runs in the same domain with the access of the same domain as the frame itself. So if the iframe came from foo.com, then the iframe, the frame came from foo.com, the script that you're downloading here, script.js, will execute as if it was coming from foo.com, even though you explicitly loaded it from bar.com. Okay. Now, same origin policy greatly reduces the number of vulnerabilities that you have. Right? So it really limits what your JavaScript can do, but it doesn't stop all the problems. So in particular, we may have vulnerabilities. We may have bugs in the same origin policy code. Okay? We may have bugs in the renderer process. So the renderer process is a process that actually looks at the HTML and other things and puts it on a nice page, and it's associated with that particular page. So what you can do as an attacker is try to bypass these same origin policies to still attack other websites. And to prevent this, the Google Chrome team set out to on a very ambitious project to make this much harder. And this is known as site isolation. The measure that they came up with is site isolation, and it ensures that all the pages, all the frames from different websites are rendered in different processes. So you no longer have this shared process where a number of different frames run at the same time, and everything is isolated in a separate process. Okay. It also, once you have that, you have everything running in separate processes, and you're using the operating system's isolation capabilities to block accesses to process, cross-process accesses that shouldn't be allowed. You can also, vet the accesses that it's trying to make and block certain the access to certain data. Let's have a look at what this looks like. Okay, so what we're assuming is a threat model where the renderer engine, so like I said, this is, you have a browser engine, which is the, if you want, the main browser, which runs almost like an operating system. And then, you have all of these sites running in different processes, different renderers that take care of, displaying this, stuff on the screen. There's also, a JavaScript engine and so on. But let's just assume that we're talking about the renderer engine. Unfortunately, renderer engines are quite complex and they have a lot of vulnerabilities. Okay. Another problem that we have is that some vulnerabilities don't really care too much about the isolation in say a process, right? So if you have a JavaScript running in a virtual machine, the vulnerabilities that have emerged recently in processors, right? So that have to do with transient execution, speculative execution. They don't care about these boundaries, right? So they can read data fairly arbitrarily. So trying to prevent attackers from abusing these kinds of advanced capabilities is really complicated. And what the Chrome team came up with is known as site isolation. Okay, and it's complex, so it required a lot of changes in the browser. But nowadays it's deployed quite universally. It has some limitations, but it's actually quite powerful. Okay, let's illustrate this briefly. Don't want to go into too much detail. In the old days, we had this browser process, and then we had a renderer process for one particular site, which could well include a frame with something else. So the renderer process of evil.com in this particular case embedded youtube.com. Now, if there was a bug in the renderer process, and basically meant that evil.com could use a universal cross-site scripting bug to bypass the same origin policy within the renderer process, or it could use a compromised renderer process to execute anything it wanted in the renderer process and access all sorts of stuff, also from other sites. Okay. Moreover, what we could have is one of these attacks based on these new speculative or transient execution vulnerabilities, such as Spectre or MDS Riddle, or there are some others, and that also allows you as an attacker to access data across security boundaries. Okay, so to leak data across security boundaries, and it has to do with all sorts of optimizations that are needed to make processes fast nowadays. And to do that, the processor executes code before it knows whether it actually needs to be executed. For instance, if you have a branch, right? So rather than waiting until you know whether the branch should go left or right, what the processor will do is say, well, it went right the last 10 times. It will probably go right again. Let me start executing this ahead of time. And then at some point, there will be a resolution, and the processor is going to look at the result and say, wait a minute, I shouldn't have gone right, I should have gone left. All of this computation that I've done on the right-hand side is all to no avail, and I have to squash the results. And that's exactly what the processor will do. It will squash the results. Unfortunately, the transient execution so the instructions that have been executed during this speculative execution, they still leave traces. They still leave traces in the microarchitecture. For instance, if you have an instruction that is speculatively executed because you thought the branch was going to go right, and you execute some instructions and they load data into the cache, that data is still going to be there, right? The results of your computation may have been squashed, but the data is still in the cache. So that means that if you measure the access time to such data, you'll see that it's fast, right? So as an attacker, you can use this to leak sensitive information by seeing whether something is accessed more efficiently than something else. It basically means that it's in a cache, and that means that that must have been accessed in this transiently executed instruction. Well, you're going to get a lot of information about transient execution attacks in hardware security. It's not a main topic for CNS. All I want to say is that these kinds of vulnerabilities are very problematic because they can also be launched from the browser. Okay. So the Chrome team wanted to use site isolation to make all of these attacks more difficult. And site isolation, and that's the main thing I want to say about this, because I also don't want to go into too much detail here, but site isolation makes sure that everything that comes from different sites, different servers, runs in a separate process. So if you have your evil.com page that embeds youtube.com, we separate these two and make sure that the youtube.com content is in a separate renderer process, so it's out of process. Okay. And then you have isolation, so even if you have a vulnerability here, you cannot easily access the content of youtube.com. Moreover, there are now possibilities to do strict access control on the kind of content that you can get from a certain web page, right? So you may be able from foo.com to access other resources from foo.com, or because this is historically the way we do things, you should be able to access scripts and images from other places also. All of that is fine, but you can stop the access to cross-site data, for instance. Okay, you can stop also some other things. Oh, and I think I'll get there in a minute. Okay, so like I said, we're placing this content out of process, and we still want to be able to do the kind of things that we did in the past. We will still want to be able to work with iframes. We want to do secure compositing. We want to do make sure that there are frame proxies so that we can actually do these kind of things. I don't want to get into this, but it's a lot of challenges for the browser implementation in order to pull this off. It sounds like obvious little thing. We put this in a separate renderer, separate process, and we're done with this. It's not so easy. Okay, so doing this well and doing it efficiently is difficult. But like I said, once we have this, we can also try to regulate the kind of accesses that you can make from your domain. So like I said, from foo.com, we can access foo.com. We can also access images from other websites, but we can perhaps stop certain accesses to data, right? And we can access certain accesses that have been mislabeled. For instance, we're trying to load something as if it's an image or as if it's a script, which is not an image or a script, right? Maybe it's a JSON file or something. Okay, so that's the kind of things that we want to do, and it actually makes it harder to access resources that you shouldn't be able to access. So site isolation has become an important protection against all sorts of attacks. Okay, and it allows the browser process to operate much like an operating system, right? So now we have an operating system. Or we have a browser process that has a number of processes running, and it regulates the accesses and the IPC, the inter-process communication that is possible, just like a real operating system would do this for its programs that are running. Okay, so for instance, you can limit the kind of access that you give to a particular process. Okay, and if it misbehaves, you can terminate that process. Now, site isolation was pioneered by Chrome, but is also researched quite heavily by Firefox. At the time of recording this lecture, this has been in development for a long time in Project Vision for Firefox, and testing has begun in, even at the time of recording. This is a long time ago in 2019. Okay, but at the time of recording, this is still not by default on in modern Firefox browsers. Okay, that's all I want to say about project isolation. So there are a couple of important points that I made. So there's security sandboxing for JavaScript. You can't have access to files. You can't have access to a number of other things. Then we have the same origin policy. And nowadays, we also have site isolation. The last thing I want to discuss, as promised, is AJAX. So asynchronous JavaScript and XML. And it allows JavaScript to modify a page based on the results that it gets from a server in response to a request, without the user actually needing to do anything. And it relies on two basic concepts, which is manipulation of the document object model, so the DOM that we talked about earlier, and something that is added to JavaScript, which is known as the XML HTTP request object. Not the most convenient name, perhaps. So the XML HTTP request object was introduced to allow JavaScript to retrieve XML data from a server independently, okay, by executing queries from JavaScript. Now, initially, this object had to be accessed in different ways depending on your browser, because Microsoft decided to do things differently from other browsers. So most browsers would simply do, XML HTTP request object, but the old Internet Explorer had something else. So we don't want to talk about this anymore. ActiveX objects are dead. Fortunately, this is no longer an issue, but you still find this code on many web pages, as we shall see in a minute. So what you can do is you can access web pages and then do certain things based on the onReady state change property of an XML HTTP request object. Okay. For instance, you can run some specific JavaScript code whenever the onReady state change when there's a change in the state. Okay, so for instance, what you can do is you can do a get of a web page and wait for the return, and you basically indicate that with true, you indicate that the request is asynchronous. So the execution of JavaScript will simply proceed while in the background this document is downloaded. Okay, and then so in this function that we registered earlier here, this function will be called whenever anything changes in the request status. For instance, when it's loading, or when it's loaded, or when the entire object is completely initialized, then we get a callback there. And the function can do anything, right? So maybe while it's loading it can do stuff, but typically it will wait until the status is complete. So you can do you can query the status by checking it, right? So see if it's 4, and then you operate on data, and else nothing is happening, so you can just return. After you've received the document and you looked for it to have been successful, you can now do an access to the content. And the content you can obtain as a string by calling the response text, or as an XML document object. Okay, so anyway, I don't want to give a tutorial on this. I just want to maybe illustrate this by way of an example. And the example is taken from some website where they wanted to build a pizza service that is customer friendly. So the customer friendly pizza service allows customers to specify the pizzas that they want to order, and also their addresses. Okay. So on the web page, you can enter your phone number and your address and your order. Your phone number, your address, and the pizza that you want to order. That's what it wants to do. And what we see here is that whenever this changes this value, your phone number, you get a call to get customer info. Okay, so as soon as the user starts to fill in his phone number, we actually call some JavaScript. Okay, great. What does that do? Well, the get customer info is here. It will look for the value of that phone number that the user has just been typing in, and craft a URL that contains where it needs to be sent to, but also the phone number as a parameter. So it's a get request. It creates a get request and sends it off to the server, right? So now it sends a new request from JavaScript to the server, and it says that if we get any updates on the status changes, call this function update page, right? And what does update page do? Well, update page simply says the server is done. It doesn't actually, it's not necessarily done, but it actually is, there's been an update at least. Okay, so that's what the update page will do. And here above this part we didn't discuss yet. Here we see that we create one of these XML HTTP request objects. So request is a new XML HTTP request object, and it also contains some legacy code for really old browsers. Okay. So let's ignore this. And the request is used here. So the request, the XML HTTP request object, is used here to fire off this request, and also to do the to register the callback whenever anything changes. Okay. Now, update page is probably not what a pizza service would really do. At least it wouldn't just say server is done. What do we want? We want something more interesting there. Okay, for instance, first of all, we're going to wait for the ready state to be complete, right? So we wait until it's 4, and we then also check whether or not it was successful. In that case, the server is done. But that's not what we want either. What we really want is to do something interesting, right? For instance, whenever we've typed in the phone number, we send off this request. Let's see, where did we go? We send off the request to our server to look up this customer by phone number, right? So the pizza server is now looking through its database, and it sees that, oh, this phone number belongs to Herbert Boss, and Herbert Boss lives at this and this address and loves this particular type of pizza, right? So that means that we can now use the reply. So once the server has figured this out, it sends that back as a reply, and it fills this. It allows the code on the client side, so the JavaScript code there, to fill in these boxes for us. So there is a pre-filled box that contains my address and my favorite order. Okay, so here we see what that looks like. So now we again check for the ready state. We check for the status code. And we see that there's a response text that we split up, right? And the response text contains an order and an address, right? So we now look for the element by ID in our document object model, and if we find an order there, we now fill in, that part of the response. We also, in our document object model, look for the address, and if we find that there, we actually fill in that part of the response. Okay, so this is a much more customer-friendly way of doing your pizza delivery service. I only need to type in my phone number, and everything gets pre-filled in automatically. Super cool. So this is all I wanted to say about the basics of the web, right? So we didn't talk too much about attacks and security issues, but we now have some notion of how the interactions on the web occur on the server side and on the client side, and some interaction between those two with Ajax. Now let's move to the